Tonight, we are going to sit quietly with a star you have known your whole life, and we are going to discover that you barely know it at all. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Now settle in, soften your breathing, and let your eyes grow heavy as we drift outward, far above the rooftops, far above the clouds, until our pale blue world becomes a small marble suspended in the dark. From here, the sun is no longer the gentle warmth on your skin. It is a vast sphere of glowing plasma, almost 1,000,000 miles across, holding our entire solar system in place with the soft, steady pull of its gravity. If you could shrink our planet down to the size of a single pea, the sun beside it would be a beach ball more than 2 feet wide. It contains more than 99% of all the matter that orbits within its reach. Every planet, every moon, every comet, every drifting grain of dust is, in a sense, just a tiny fleck circling around this one enormous, glowing heart. And yet, for all its size, for all its closeness, the sun is still one of the strangest objects we have ever tried to understand. We have stared at it for thousands of years. We have measured its light with delicate instruments. We have sent spacecraft skimming closer to its surface than anything ever made by human hands. And still, when scientists gather to speak honestly, they admit something quiet and humbling. We do not fully know how the sun works. There are questions about our star that have remained open for decades. Some have remained open for more than a century. The most famous of them sounds almost too simple to be real. The visible surface of the sun, the part we see as that bright disk in the sky, glows at around 10,000 degrees Fahrenheit. But the thin, ghostly atmosphere above that surface, the part called the corona, reaches temperatures of more than 1,000,000 degrees. The outer air of the sun is hundreds of times hotter than the surface beneath it. No one yet knows exactly why. It would be like standing beside a campfire and finding that the air far above the flames is somehow hotter than the burning wood. The arrow of heat seems to point in the wrong direction. There are theories. There are good ones. Some researchers wonder if tiny, countless magnetic explosions, too small for us to see clearly, are heating the corona from below. Others suspect that waves rippling through the sun's tangled magnetic field carry energy upward and release it high above the surface. The evidence so far points to both ideas being partly right and partly incomplete. There is another mystery just as old. The sun has a rhythm. Roughly every 11 years, it grows stormier, then quieter, then stormier again. Sunspots come and go. Magnetic poles flip. Flares brighten and fade. But the rhythm is not exact. Sometimes the cycle runs long. Sometimes it runs short. Sometimes, in centuries past, the cycle seemed to almost stop altogether, and the sun grew strangely quiet for decades on end. We still cannot predict with confidence what the next cycle will bring. We do not know what truly drives the engine beneath. Tonight, we are going to wander slowly through these questions. We will hover over the boiling, granulated surface, where bubbles of hot plasma the size of countries rise and fall in just a few minutes. We will drift through the strange silver light of the corona during an eclipse. We will follow the solar wind out past the planets into the bubble it carves through interstellar space. We will sit with the puzzle of the missing neutrinos and the long silence of the Maunder minimum and the quiet songs the sun sings in vibrations only our instruments can hear. And through all of it, the goal is not to give you answers. The goal is to let you rest beside the questions, to let the open mystery of our nearest star become a soft, slow companion as you fall asleep. There is something deeply restful about admitting how much we still do not know about something so close, so familiar, so present in every sunrise we have ever seen. So let your shoulders drop. Let the day go. The sun has been burning for about 4.5 billion years, and it has kept its deepest secrets the whole time. There is no hurry. We have all night to wonder. Let us start with the simplest picture of the sun, the kind a child might draw. A round, glowing shape in the sky. Yellow, maybe orange, with little rays poking out around the edges. That drawing is not wrong. It is just missing almost everything. The sun is a star. It is the only star close enough for us to see as a disk, instead of a point. Every other star in the night sky is so far away that even our best telescopes show them as tiny pricks of light. The sun is different only because it is near. If you could pull it back to where the other stars live, it would vanish into the same scattered dust of distant suns. In size, it is hard to picture. The sun is about 864,000 miles wide. You could line up 109 Earths across its face and still have a little room left over. If the sun were a hollow ball, you could pour more than 1,000,000 Earths inside it. And yet, among stars, it is fairly average. Many stars are smaller. Many are far, far larger. It sits about 93 million miles away from us. Light, which moves faster than anything we know, still takes about 8 minutes and 20 seconds to cross that gap. So, the sunlight warming your face right now left the sun before you sat down. If the sun blinked out this very second, we would not know for more than 8 minutes. We would keep going about our lives, bathed in light from a star that was already gone. The sun is old, though not as old as the universe. Its age is roughly 4.5 billion years. That is about a third of the age of everything. It was born from a slow collapse of gas and dust, the leftover ingredients of older stars that lived and died before it. Some of the atoms inside the sun were forged in stars that no longer exist. Some of those same atoms are in you. What is the sun actually made of? Mostly two things. About 3/4 of its mass is hydrogen, the lightest and simplest element. Most of the rest is helium, the next lightest. A small sprinkle of heavier elements makes up less than 2%. Carbon, oxygen, iron, nickel, and many others, all in trace amounts. But there is no rock here, no solid ground. The sun has no surface you could stand on. It is a ball of gas so hot that its atoms have been torn apart into a state called plasma. A soup of charged particles, neither fully gas nor liquid, nor anything else we meet on Earth. The heat is staggering. The visible surface, the part we see in photographs, glows at about 10,000 degrees Fahrenheit. The center, where the energy is made, reaches around 27 million degrees. To picture that, imagine the hottest oven in any kitchen. something more than 50,000 times hotter. The numbers stop meaning much. They simply mean hot beyond any human experience. And yet, here is where the story turns strange. Above the bright surface, far from the blazing core, the sun's outer atmosphere begins. It is called the corona, which comes from the old word for crown. During a total eclipse, you can see it as a soft, pearl-colored halo around the dark disk of the moon. The corona is thin, ghostly, beautiful, and it is hotter than the surface beneath it. Far hotter, hundreds of times hotter. In places, more than 1,000 times hotter. This makes no sense at first. Imagine standing near a campfire. As you walk away, the air gets cooler, not warmer. Heat should fade as you leave the source. But on the sun, somewhere between the surface and the high corona, something is pouring energy upward against all common sense. The crown of the sun burns far brighter in temperature than the body it sits upon. This is the riddle that will run through the rest of our night together. We call it the coronal heating problem. We have known about it for more than 70 years. We have sent spacecraft closer to the sun than ever before. We have built better and better instruments. And still, the question is open. There are theories. There are clues. There are pieces of an answer. But no one yet can say with certainty why the sun's outer atmosphere is the hottest part of the star. For now, hold that small mystery in your mind. A glowing ball, average among stars, with a crown that burns hotter than its face. We will sit with it for a while. The bright face we see when we glance toward the sun is only a thin skin. Beneath it lies a vast hidden country, layered like the rings of an old tree, each layer holding clues to how our star came to be. The light that warms your window this morning began its life deep below, in a place no telescope can ever directly see. To understand what lies beneath that glowing surface, we have to travel backward in time to a moment before the sun existed at all. Roughly 4.5 billion years ago, there was no sun. There was only a great slow cloud of gas and dust, drifting in the quiet between older stars. The cloud was mostly hydrogen, with traces of helium and a sprinkling of heavier dust grains. These grains were the ashes of stars already lived and died, scattered across the dark like seeds. The cloud was cold and patient and enormous. Something began to disturb it. Some researchers think a nearby star ended its life in a great explosion, sending a shockwave through the cloud. Others wonder if the cloud simply grew too heavy to hold itself up and started to collapse on its own. We do not know for certain which trigger pulled the first thread. The evidence is incomplete, hidden under billions of years of change. Whatever the cause, the cloud began to fall inward. As it fell, it spun. As it spun, it flattened into a slow disk with a thickening knot at its center. That knot grew warmer as more material piled onto it. Pressure rose. Heat rose. Inside the knot, atoms began bumping each other harder and harder, their motion building into something fierce. For a long stretch of time, perhaps tens of millions of years, this young sun was not yet truly a star. It was a glowing ball of compressed gas, shining only from the heat of its own collapse. Then, at the very center, the conditions finally crossed a quiet threshold. Hydrogen atoms began to fuse into helium. Nuclear fusion lit the core, and the sun became a star. That moment of ignition is the deepest layer of the mystery. We cannot see the core directly. Light born there takes 100,000 years, by some estimates, to wander its way out to the surface. The journey is so slow because the inside of the sun is densely packed, and each tiny photon bounces from particle to particle, drifting outward at the pace of a forgetful traveler. By the time that light reaches your eyes, it has crossed the inside of the sun for longer than humans have existed. Above the core sits the radiative zone, where energy moves by radiation through plasma, so dense it behaves almost like a thick syrup. Above that lies the convective zone, where the plasma boils. Hot material rises, cools, and sinks again in vast, slow cells that churn like a pot of stew the size of a planet. The surface we see, called the photosphere, is simply the top of this boiling layer, the place where the gas finally becomes thin enough for light to escape into space. But here the questions begin to gather. We have models of how the inside of the sun should behave, and many of those models match what we measure On the outside, sound waves ripple through the sun, and by listening to them, we have learned the rough shape of its hidden layers. Yet, some details refuse to settle. The amount of certain elements deep inside the sun, especially oxygen and carbon, does not quite match what our best theories predict. Some researchers think our measurements of the surface are slightly off. Others wonder if our models of the interior are missing a piece. The disagreement is small, but it is stubborn. There is also the question of how evenly the sun rotates beneath its surface. The outside spins faster at the equator than at the poles. Inside, the pattern shifts in ways that surprised the first scientists who measured it. Why the interior turns the way it does, and how that turning shapes the magnetic forces above, remains an open puzzle. So the sun was born from a cold cloud, lit by gravity, and woven into layers we can only partly understand. Its bright face hides a slow, churning history that began before the Earth, before the planets, before anything you could call a day. Tonight, as you settle into the quiet, picture that ancient cloud drifting in the dark, slowly gathering itself into the star whose warmth still reaches us. The story is older than memory, and parts of it are still being read. On the bright face of the sun, dark patches come and go. They drift across the surface like slow, cool islands in a sea of fire. We call them sunspots. They have been watched for centuries, sketched by hand long before we had telescopes that could safely look at the sun. And yet, after all this time, the slow heartbeat of these dark spots is still not fully understood. A sunspot is not really dark. If you could lift one out of the sun and set it alone in the sky, it would glow brighter than a full moon. It only looks dark because the surface around it is hotter and brighter still. A sunspot is a place where the sun's magnetic field has grown so strong that it slows the rising heat below. The plasma there cools by a few thousand degrees. In the bright bath of the surrounding surface, that cooler patch reads as a shadow. The stuff that makes up these spots is the same stuff that makes up the rest of the sun. Mostly hydrogen, the simplest atom in the universe. A single proton with a single electron, the first element to form after the early universe cooled. Hydrogen makes up about 3/4 of the sun by mass. Helium, the next simplest element, makes up most of the rest. Helium was also forged in those first hot minutes after the universe began, when the cosmos itself was a kind of furnace. Mixed into the sun in small traces are heavier things: carbon, nitrogen, oxygen, iron, silicon, magnesium, neon. These are the same elements that shape the bodies of planets and the bodies of living things. None of them were here at the start. They were built inside stars that lived and died long before our sun was born. The iron at the heart of the earth, the calcium in your bones, the oxygen you are breathing right now. All of it was cooked in the cores of ancient suns. When those suns ended, they scattered their elements across vast clouds of gas. Our sun gathered some of those ashes when it formed. So did the planets that circle it. This is why sunspots, for all their strangeness, are made of star ash too. The plasma inside a sunspot is the same recycled matter that built everything around you. The difference is the magnetic field. Inside a sunspot, the field can be thousands of times stronger than the field around the Earth. It threads through the plasma like invisible rope, holding it, twisting it, choking off the rising currents of heat from below. How these magnetic ropes form, and why they emerge in such regular patterns, remains an open question. One leading idea is that the sun's inner layers, which rotate at different speeds, stretch and wind the magnetic field like dough being kneaded. Over years, the field grows tangled and strong until loops of it break through the surface and create the dark spots we see. A competing view suggests that the action happens closer to the surface, in a thinner layer near the top of the sun's convection zone. Both pictures explain some of the observations. Neither explains all of them. The spots themselves come and go on a slow rhythm. They build up over years, peak in number, then fade again. This is the famous 11-year cycle, though it is not always exactly 11 years. Some cycles are shorter, some are longer, some are strong with many spots, some are strange and quiet. The sun has had stretches in its past when sunspots almost vanished for decades. We do not know in any deep way what sets the pace. What we do know is that the heartbeat is real and that it touches us. Sunspots are nurseries for storms. Around them, the magnetic field can snap and reconnect, hurling plasma outward in great bursts. These bursts ride the solar wind across the gap between the sun and the earth. They tug on our magnetic field. They light up the polar skies in green and red curtains of aurora. They are the visible end of a long thread that began deep inside the sun, in places we cannot see. When you look at a sunspot, you are looking at a knot of star ash held together by a force we can measure, but cannot fully predict. The hydrogen inside it is older than the planets. The iron inside it is older than the sun. The magnetic field shaping it is younger than yesterday's weather, yet rooted in something the sun has been doing for billions of years. The spot will drift, fade, and vanish. Another will rise to take its place, and we will keep wondering gently what sets the rhythm of this slow, dark heartbeat. If you could look at the sun through a very careful telescope, with all the right filters in place, you would not see a smooth yellow ball. You would see something stranger. The surface would look like it was covered in tiny golden grains, packed together edge to edge, each one shimmering and shifting in slow motion. These are called granules, and they are one of the gentlest, most quietly amazing things about our star. Each granule is a bubble of hot plasma rising from below. Hot material pushes up from the deeper layers, spreads out across the top, cools just a little, and then sinks back down along the dark edges of the bubble. It is the same kind of motion you can see in a pot of soup simmering on a stove. Hot fluid rises in the middle, cools at the surface, and sinks at the sides. The sun does this everywhere, all the time, across its entire face. The size of a single granule is hard to picture. One bubble is often about 1,000 kilometers across. That is wider than many countries on Earth. And yet, against the vast scale of the sun, each granule looks like a tiny grain of sand on a beach. There are millions of them at any moment, and each one only lives for about 8 to 20 minutes before it fades, and a new one takes its place. The forces that drive this dance are simple to name, but hard to fully understand. deep inside the sun, heat wants to escape. Nuclear reactions in the core release enormous energy. That energy slowly works its way outward, first as light bouncing through dense plasma, then as moving currents of hot gas. The outer third of the sun is called the convection zone. There, the gas is cool enough, and the conditions are right for it to flow in great churning loops, like water boiling under a low flame. Gravity pulls everything downward. Pressure from below pushes everything upward. Heat tries to spread. Magnetic fields tug and twist. All these forces meet at the surface and produce the granules we can see. The bright centers are rising hot plasma. The dark lanes between them are cooler material sinking back down. The whole pattern is in constant motion, like the skin of a living thing. There is another, larger pattern layered on top of the granules. Some researchers call them supergranules. They are much bigger, often 30,000 kilometers across, and they live for a day or two before fading. Why these larger cells exist at all is still being debated. One idea is that they are simply a deeper, slower form of the same boiling motion. Another idea is that they are something different, shaped by forces we have not fully mapped yet. The honest answer is that the sun has more than one rhythm running at once, and we are still learning how those rhythms fit together. Magnetic fields make the picture even more complicated. The rising and sinking plasma carries magnetic field lines with it. As the granules churn, they drag these field lines around, tangling them, stretching them, sometimes pinching them into bright knots. These small magnetic knots may play a role in heating the layers above. Some researchers think that countless tiny magnetic events, each one too small to see clearly, add up to feed energy into the corona. Others think the main source of that heat comes from larger waves traveling outward through the plasma. The question is open. The granules may be quietly involved in the answer, or they may be a side effect of something deeper. What is striking when you sit with the image is how soft and steady the whole process is. The sun is not exploding. It is breathing. Each little granule is a slow exhale of energy from the deep core, carried outward over hundreds of thousands of years, finally reaching the surface and releasing its warmth into space. By the time the light from a granule reaches your eyes on Earth, the energy inside it has already been on a very long voyage. We have watched these grains for over a century. We have filmed them, modeled them, simulated them on powerful computers. And yet, there are still things about them we cannot fully explain. How exactly do the smallest magnetic features form? How do the granules and supergranules interact with the layers above? How much of the sun's quiet, constant brightening and dimming comes from this slow boiling motion at the top? For tonight, it is enough to picture it. A great calm sphere covered in soft golden grains, each one rising and sinking in its own short life, while the star beneath them keeps its older, slower secrets. If you could lift away the blinding light of the sun and see only its magnetism, you would not see a smooth, simple bar magnet. You would see something closer to a tangled forest of glowing threads, loops within loops, arches that rise and twist and snap, a web so vast and so finely woven that no instrument we have built can trace it all at once. This is the magnetic field of the sun, and it remains one of the most beautiful unsolved puzzles in our sky. To feel the scale of it, start with the sun itself. If you shrunk the sun down to the size of a basketball and set it on a quiet table, the earth would be a single peppercorn rolling along the carpet about 26 yards away. Jupiter would be a small marble more than a football field from that basketball, and the magnetic field reaching out from that basketball would stretch in some directions past every planet in the room and well beyond the walls of the house. It is not a small thing pretending to be large. It is a truly enormous structure, and most of it is invisible. Now zoom back in. The sun's actual diameter is about 865,000 miles. You could line up 109 Earths across its face and still have room to spare. Inside that vast sphere, the magnetic field is born in motion. Hot plasma, gas so hot its atoms have come apart into charged pieces, churns and flows in deep currents. Those moving charges create magnetism, the way a river dragging iron filings might trace patterns on a sandy bed. The result is a field so complex it defies simple description. At the surface, the field gathers itself into bundles. Some bundles are small, no wider than a small town on Earth. Others are giant ropes thousands of miles thick, anchored deep below and arching high above. The smallest magnetic features we can clearly see are still about 60 miles across, which sounds tiny until you remember they are 60 miles of glowing plasma standing on the face of a star. Below that scale, the web grows finer than our telescopes can resolve, and we are left guessing at what the smallest threads look like. The strength of these threads is just as hard to imagine. The Earth's own magnetic field, the one that nudges a compass needle, is gentle. A fridge magnet is about 100 times stronger than the Earth's field at the surface. A sunspot's core, by contrast, can be thousands of times stronger than that fridge magnet, packed into a region wider than our entire planet. Holding that much magnetic energy in one place is like coiling a spring the size of a continent. When it slips, the release is felt across the solar system. The web reaches farther than the sun's visible body by an almost absurd margin. Magnetic field lines, carried outward by the solar wind, stretch past Mercury, past Venus, past Earth, past Mars, past the asteroid belt, past Jupiter, past Saturn, past Neptune. They keep going until they finally lose their grip somewhere beyond the orbit of Pluto, in a region where the sun's influence fades into the colder magnetism of the galaxy itself. If the sun were a basketball on that quiet table, its magnetic bubble would fill a sphere larger than a small town. And yet, for all that size, we cannot truly map it. We see slices. We see the footprints where field lines pierce the surface. We see the bright loops glowing in ultraviolet light high above. We see the long streamers reaching into space during an eclipse. But the full three-dimensional shape of the web, moment by moment, escapes us. Our best models are educated guesses, stitched together from limited views. One theory holds that small, rapid magnetic tangles deep in the surface layers shape the larger pattern from below. A competing idea suggests the great pattern is set by deep currents far beneath, and the small tangles are only the visible foam on a much deeper sea. Both ideas have evidence. Neither is settled. What stays with you when you sit with these numbers is the strange mix of nearness and unknowability. The sun is right there, only 8 light minutes away, close enough to warm your skin on a summer afternoon. And yet, its magnetic web, the very thing that drives its weather, heats its outer crown, and shapes the bubble we all live inside, remains a map with most of the lines drawn in pencil, faint and provisional. Our nearest star wears a coat we still cannot quite see. Woven on a loom we are only beginning to understand. Imagine for a quiet moment that you could float above the sun, not too close, just far enough to watch in safety, suspended in the dark. Below you, the bright face of the star churns and shimmers, a sea of golden plasma in slow motion. Above you, there is no clear boundary where the sun ends. The star simply fades outward, thinning into a glowing haze, and then into something stranger still. That haze is moving. It is always moving. A steady breath of charged particles pours out from the sun in every direction at once, racing past you, past the planets, past the icy edge of the solar system. We call it the solar wind. It never stops. It has been blowing for billions of years, and it will keep blowing for billions more. If you could see this wind with your own eyes, it would look almost like a soft, glowing fog, pale gold near the surface, fading to a ghostly white as it streams outward. In some places, it moves slowly, drifting at a few hundred kilometers per second. In other places, it rushes much faster, twice that speed or more, gusting from dark patches on the sun called coronal holes. The wind is not smooth. It is gusty, knotted, threaded with magnetic fields that twist and snap as they go. For decades, one of the deepest puzzles about this wind has been a simple question. How does it get up to speed? The sun's gravity is enormous. It should hold these particles back, slowing them as they climb away. And yet, by the time the solar wind reaches Earth, it is moving at hundreds of kilometers every second, far faster than gravity alone would allow. Something is pushing it. Something is heating it, accelerating it, giving it the energy to escape. We do not fully know what that something is. One leading idea points to magnetic waves, The sun's surface is alive with shaking, ringing motion, and that motion can send waves rippling up along magnetic field lines. These waves, called Ulfen waves, may carry energy outward and dump it into the thin gas above, pushing the particles faster as they climb. Some recent measurements seem to support this picture. The Parker Solar Probe, a small spacecraft that has flown closer to the sun than anything before it, has measured these waves curling and snapping in the inner solar wind. But another idea offers a different answer. In this view, the wind is accelerated by countless tiny magnetic explosions. Near the surface, small bursts of reconnection where field lines break and rejoin. Each burst is gentle on its own. Together, they may add up to a constant outward push. The Parker probe has seen strange little kinks in the magnetic field, called switchbacks, that some researchers think are the fingerprints of these tiny events. It may be that both ideas are partly right. It may be that neither is quite right. The question remains open. What we do know is that this wind shapes the space around every planet. It carves the tails of comets into long, glowing streamers that always point away from the sun. It pushes against the magnetic field of Earth, squeezing it on the day side and stretching it into a long tail on the night side. When the wind gusts hard, it stirs up auroras at the poles, soft curtains of green and red light dancing in the cold air. If you stood on the moon, with no atmosphere to shield you, the solar wind would be brushing across the dust beneath your boots. It has been doing that for billions of years, slowly changing the chemistry of the lunar surface, baking the soil with hydrogen and helium from the sun. And the wind has a boundary, far out beyond the planets, where it finally slows down and meets the thin gas between the stars. We will come back to that bubble later in the night. For now, just sit with the picture of it. A star quietly exhaling, a steady golden breath that fills the space between worlds. Float a little closer in your mind. Watch the plasma streaming past you, warm and electric and almost silent. Feel how strange it is that we still cannot fully explain what you are seeing. We can measure the wind. We can sample its particles. We can map the places it comes from. But the deeper question, the the one about what truly drives it outward against the pull of the sun, has not yet been answered. It is one of the oldest open questions about our star, a wind that never stops, born from a process we have not yet pinned down. And tonight, while you rest, it is still blowing past the earth, soft and unseen, carrying the breath of the sun out into the dark. Far above the bright face of the sun, in the thin and shimmering layers we cannot see with the naked eye, something strange happens from time to time. A patch of the atmosphere brightens, then it brightens more. Within minutes, a region the size of many Earths begins to glow with a sudden release of energy. We call these events solar flares, and though we have watched them for over a century and a half, we still do not fully understand how they begin, why some grow gentle and others grow fast, or what hidden trigger sets them loose. The first solar flare ever recorded was seen in 1859 by a quiet English astronomer who happened to be sketching sunspots that morning. He looked up and saw two patches of brilliant white light blooming on the sun's face. Within hours, the night skies of Earth glowed with auroras as far south as the Caribbean. Telegraph wires sparked. Operators received shocks. Something invisible had traveled from the sun and touched the planet. What he had witnessed was the bright flash of a flare, paired with a wave of charged particles racing outward through space. Today, we know flares are born from twisted magnetic fields. Deep beneath the surface, the sun's churning plasma drags those fields into knots. The knots rise. They tangle. They press against one another in the lower corona until something snaps, releasing a sudden burst of energy as light, heat, and accelerated particles. That much we believe we understand. The deeper question is how the snapping happens at all. The leading idea is called magnetic reconnection. In this picture, two opposing magnetic lines drift close, touch, and rearrange themselves into a new shape. The change releases enormous energy in a fraction of a second. It sounds simple, but the details remain blurry. The physics of reconnection inside a hot, thin plasma is one of the hardest problems in modern science. Computer models can reproduce some flare features, yet none can predict when a real flare will erupt or how strong it will be. Other researchers wonder if reconnection alone is enough. Some suggest that waves traveling through the magnetic field may pile up energy in certain spots, weakening the structure until it gives way. Others propose that small flares trigger larger ones, like a slow cascade of tiny shifts building into a single great release. The competing pictures are not contradictions so much as different angles on a process. We still cannot watch closely enough. What makes flares so hard to study is their speed and their height. They happen in the corona, far above the visible surface, in plasma so thin you could pass your hand through it without resistance. Yet that same plasma reaches temperatures of millions of degrees. A flare lasts only minutes. The strongest ones release more energy than humanity has ever produced in its entire history, all in the span of a long breath. Spacecraft have brought us closer. The Parker Solar Probe, plunging again and again toward the sun, has flown through regions where flares are born. Its instruments have caught the tremor of magnetic shifts and the sudden showers of fast particles. Yet even with this nearness, the trigger itself slips out of view. The instruments measure the moment after. The moment of release remains hidden inside the tangle. There is also the puzzle of why flares vary so widely. Some are gentle, brief flickers, no larger than a continent. Others grow so vast they bend the sun's outer atmosphere into long arcs of falling plasma, the strongest known flares, sometimes paired with great clouds of charged matter called coronal mass ejections, can hurl billions of tons of solar material into space at speeds of millions of miles per hour. We can describe these events. We cannot yet say what makes one region of the sun produce a giant, while another produces only a whisper. A quiet worry sits beneath this mystery. If the largest flares are rare, but possible, then one may someday strike Earth's magnetic shield with a force we have never measured directly. Our modern world of satellites and power grids has not yet lived through such an event. The 1859 flare arrived in a world of telegraph wires. The next one will arrive in a world of fiber optics and orbiting machines. How often such giants come, and what governs their birth remains an open question. For tonight, picture the sun's outer layers as a slow, glowing sea. Somewhere within that sea, magnetic ropes are twisting, building tension we cannot see. A flare may bloom tomorrow. It may bloom in a century. The sun does not tell us, and the silence between flares is itself part of the mystery, a quiet we have not yet learned to read. Far beneath everything we have spoken of so far, beneath the corona and the flares, beneath the sunspots and the boiling granules, beneath the visible surface itself, there lies a place no eye has ever seen and no instrument has ever touched. The core of the sun, a sphere of compressed plasma, roughly a quarter of the way out from the center to the edge. Here, in the dense quiet at the heart of our star, the real engine turns. The numbers we use to describe this place feel almost unreal. The temperature is thought to be around 15 million degrees. The pressure is so great that hydrogen atoms cannot stay separate. They are crushed together until sometimes they fuse. 4 hydrogen nuclei become one helium nucleus, and a tiny sliver of mass is released as pure energy. This is the process that lights the sun. It has been lighting the sun for nearly 5 billion years. What is strange, and what is still not fully understood, is how slowly that energy escapes. A single packet of light born in the core does not simply fly outward. It is absorbed, re-emitted, scattered, absorbed again, in a long random walk through the dense layers above. By some estimates, the light reaching your window tonight may have begun its trip out of the core 100,000 years ago. Some estimates go higher. The exact number depends on assumptions we cannot directly test, and researchers still debate the correct figure. This long delay matters. It means the surface we see and the core that powers it are out of sync. The sun shining today is the result of fusion that happened in the deep past. If the core dimmed slightly tomorrow, we would not know for ages. If it brightened, the news would crawl outward at the pace of a glacier. The engine and the lamp are connected by a very long, very slow wire. The core itself is thought to rotate differently than the layers above it. Heliosismology, which is the study of sound waves moving through the sun, suggests the core may spin almost like a solid body, while the outer layers spin faster at the equator and slower near the poles. Why this difference exists is not settled. One idea is that the core has held onto the rotation rate of the young sun, while the outer layers have been slowed by the steady drag of the solar wind over billions of years. Another idea is that magnetic forces deep inside couple the layers in ways we have not yet untangled. Both pictures fit some of the data. Neither fits all of it. There is also the slow, quiet matter of the sun's gradual brightening. Most models agree that the sun shines a little more strongly now than it did when Earth was young. This is thought to be the natural result of helium building up in the core, changing the density and the rate of fusion. The change is gentle, about 1% every 100 million years or so. Yet, over the lifetime of the sun, it adds up to something significant, and it raises a puzzle we will return to in a later section about why the young Earth did not freeze under a dimmer sun. For now, sit with the rhythm of it. The core breathes on a timescale that dwarfs everything human. A heartbeat measured not in seconds, but in epochs, while civilizations rise and fall on the surface of a small blue world. The engine at the heart of the sun ticks forward by fractions of a percent. Hydrogen slowly becomes helium. The dense center grows a little denser. The fusion zone shifts, almost imperceptibly, outward. And yet, inside that immense slowness, smaller cycles ride along. The 11-year sunspot cycle, the longer cycles of weak activity and strong activity that span centuries, the wandering of the magnetic poles. None of these begin in the core, as far as we can tell. They are thought to be born higher up, in the churning zones nearer the surface. But the core sets the stage. It provides the steady output, the patient warmth, against which all the faster cycles play out. What we cannot yet do is look inside and check. Our models of the core are built from indirect clues, sound waves on the surface, tiny particles called neutrinos that slip out almost unimpeded, comparisons with other stars. The picture we have is consistent and elegant, and probably mostly right. But there are gaps, quiet places in the equations where assumptions stand in for measurements. The deepest part of our nearest star remains, in some real sense, a place we have inferred rather than seen. Tonight, the engine turns on, slow and steady, as it has for ages. For most of human history, the sun was something we could only see. Its light reached us across 93 million miles, and we watched it with our eyes, and later with telescopes, and later still with instruments that could read the colors hidden in its glow. But the sun also sends us something else, something far stranger, something we cannot see at all. It sends us neutrinos, tiny particles, almost weightless, almost ghostly. They are born deep in the core of the sun, in the same place where hydrogen fuses into helium. And once they are born, they slip out through the entire mass of the star as if it were not even there. A neutrino can pass through a wall of lead a light year thick and barely notice. Right now, as you lie still and breathe slowly, trillions of them are passing through your body. They came from the heart of the sun. They left it less than 9 minutes ago. For decades, neutrinos gave us a quiet way to listen to the sun's core. We could not see into that buried furnace. No light from the core escapes directly. The photons we see at the surface have wandered for tens of thousands of years through the dense layers above. But neutrinos travel in a straight line at nearly the speed of light, and they carry news from the deepest place. If we could catch them, we could check whether our picture of the sun's interior was right. So we built strange machines to catch them. Great tanks of cleaning fluid buried in old mines. Vast pools of heavy water shielded under mountains of rock. Detectors made of pure ice in the frozen ground near the South Pole. These instruments waited for the faint, rare moments when a neutrino bumped into an atom and left a tiny flash behind. And when the counts came in, something was wrong. The sun was sending us only about a third of the neutrinos we expected. The numbers did not match the theory. For more than 30 years, this puzzle had a name. It was called the solar neutrino problem. Some researchers wondered if our model of the sun's core was simply mistaken. Maybe the core was cooler than we thought. Maybe fusion ran in a different way down there. Others wondered if the neutrinos themselves were doing something we did not yet understand. Eventually, the second idea proved correct. Neutrinos come in 3 kinds, 3 flavors, and they can change from one kind into another as they travel. Our early detectors could only see one flavor. The others slipped past unnoticed. When new detectors learned to count all 3, the missing neutrinos appeared. The sun was behaving exactly as predicted. The strangeness was in the particles, not the star. That story still teaches us something. It shows that the sun has neighbors we never meet directly. Not planets, not comets, particles. A constant, invisible breath flowing outward in every direction, washing over Earth, washing over the cold outer worlds, washing into the dark between stars. The sun is connected to us not only by light and warmth, but by this silent rain, and the neutrinos still hold open questions. The numbers now match, but the picture is not complete. Researchers have measured neutrinos from the main fusion reaction, the one that powers most of the sun's energy. They have also caught neutrinos from a second, rarer reaction involving heavier elements in the core. The amounts seem roughly right. Yet some small differences linger between what the theories predict and what the detectors count. Whether those differences mean something deep, or whether they will fade with better measurements, remains unsettled. There are quieter mysteries here too. The sun's neutrino output should change very slightly over long periods as the core slowly shifts and ages. We have not been watching long enough to see that change. We are listening to one short moment in a very long song. Future detectors, larger and more sensitive, may pick up patterns we cannot yet hear. Some researchers wonder if the neutrino count varies in subtle ways across the 11-year cycle of sunspots. Most evidence says it does not. But the question has not been fully closed, so the neutrinos remain our nearest neighbors from the sun's hidden interior. They arrive without sound, without light, without weight you could feel. They tell us that the furnace at the center is burning the way we think it is. They also remind us how much we learned only by being wrong for a long time, and how the answer came from a direction no one quite expected. The sun's core is still speaking. We are still learning how to listen. Space is silent. No air carries sound between the stars, so the sun should be the quietest thing in the sky. And yet, in a strange and beautiful way, our star is ringing. It hums, it pulses, it vibrates with deep, slow notes that no ear could ever catch, but that our instruments have learned to hear. The sun is not solid. It is a vast ball of hot gas, layered like an onion, and that gas is in constant motion. Bubbles of hot plasma rise from below. Cooler material sinks back down. These churning movements send pressure waves rolling through the sun's interior. The way a struck bell sends sound through metal, the whole star quivers with millions of these waves at once, each one a tone, each one a slow song the sun is singing to itself in the silence of space. The notes are far too low for human hearing. A single oscillation can take 5 minutes to complete. If you sped them up, the sun would sound something like a deep, soft chord, layered and shifting, with no clear beginning and no clear end. Scientists who study this hidden music call their field heliosismology, which simply means listening to the quakes inside the sun. By watching the surface rise and fall by tiny amounts, researchers can map what is happening deep inside. The waves bend as they pass through hotter or cooler regions. They speed up and slow down. They reveal layers and currents that no telescope could ever see directly. In this way, the sun's silent songs have become one of our only windows into its hidden interior. And what those songs have shown us is genuinely strange. There are rivers of plasma flowing inside the sun, slow and steady, like ocean currents made of fire. There are bands of faster rotation near the equator and slower rotation near the poles. A pattern called differential rotation that no one fully understands. There are signs of vast flows that may carry magnetic fields from one part of the sun to another over decades, perhaps driving the long cycles we see on the surface. The extremes here are almost beyond imagining. The sun's core reaches around 15 million degrees Celsius, hot enough that hydrogen atoms fuse into helium and release the light that warms our world. The pressure at the center is more than 200 billion times the air pressure at sea level on Earth. A sugar cube-sized piece of the core would weigh about as much as a small car. And yet, even at those crushing depths, the slow songs of the sun travel through, carrying information all the way to the surface. The corona, the sun's outer atmosphere, sits at the other extreme. There, the temperature climbs to more than 1,000,000 degrees, sometimes several million, while the surface beneath it sits at a relatively cool 5,500. No one has fully explained how this can be. One idea holds that the corona is heated by countless tiny magnetic explosions, far too small to see individually, that together pour energy upward. Another idea suggests that magnetic waves, born deep inside the sun and carried outward, dump their energy into the thin corona and set it ablaze. Both ideas have evidence. Neither has won the argument. The solar wind, the steady stream of particles flowing out from the corona, reaches speeds of more than 700 kilometers per second in its fastest streams. That is more than 2.5 million kilometers per hour. The slowest streams still move at hundreds of kilometers per second. How exactly the wind is accelerated to such speeds, and why some streams move so much faster than others, remains an open puzzle. The Parker Solar Probe, flying closer to the sun than any spacecraft has ever gone, is still gathering clues, and the sun's magnetic field, that invisible architecture shaping everything, flips its north and south poles roughly every 11 years. A switch of that scale on something so enormous seems like it should be loud, but it happens quietly, deep in the churning interior, where the songs of the sun travel and bend and tell us only fragments of the story. So picture our star glowing soft and steady in the dark, and imagine the slow chords moving through it. Imagine the rivers of plasma, the trembling surface, the silent music that fills its body. We have learned to listen, just barely. We have caught a few notes, sketched a few patterns. The full song, with all its hidden verses, is still mostly unheard. The sun goes on singing in silence, and we go on trying to understand what it is saying. For centuries, we have looked at the sun from the side. Every spacecraft we sent every telescope we built, every careful drawing across hundreds of years. Almost all of them saw the sun from the same flat angle. We live near the middle of the solar system, spread out along a thin disk, and the sun spins more or less along that same plane. So we see its belly, we see its equator, we watch the sunspots drift across its middle like slow ships crossing a wide sea. But the top of the sun and the bottom of the sun remain almost a stranger to us. The poles of the sun are quiet places. They do not throw out the big tangled sunspots we see at the equator. They do not flicker with the same loud bursts. They seem calmer, smoother, almost shy. And yet, they may hold the key to one of the deepest puzzles about our star. The magnetic field at the poles flips during each solar cycle. Whatever happens up there at the crown and down there at the foot seems to set the rhythm for everything else. We just have not had a good view. Only one spacecraft ever climbed high above the sun's plane to look down on it from the side decades ago. And even that mission could not see the polar surface with sharp eyes. It measured the wind and the magnetic threads passing by. But the actual face of the pole stayed hidden. More recently, a new probe has begun tilting its orbit, slowly lifting itself out of the flat plane to glance at the polar regions for the first time with modern cameras. The early images are faint and strange. The poles do not look like the equator. Tiny bright points scatter across them like grains of sugar spilled on dark cloth. These small bright points are one of the quiet wonders scientists love. Each one is a little magnetic doorway, a place where a thread of the sun's hidden field pokes through the surface. At the equator, these threads cluster into the dark spots we know so well. At the poles, they appear smaller, more delicate, more numerous. Some researchers think these tiny magnetic doorways may be where the slow, steady solar wind begins its long climb outward. Others suspect the wind comes mostly from larger open patches nearby, and the bright points are just decoration. The matter is not settled. The polar light itself has a different texture. Near the equator, the sun's surface boils with granules, each one about the size of a country, rising and sinking in a minute or two. The granules at the poles seem to be there too, but they appear stretched and tilted, as if seen through a different lens. Part of this is simply the angle of our view. Part of it may be something real about how the gas moves up there. The sun turns faster at its middle than at its poles. A slow, lazy difference called differential rotation. And that uneven spin must do something gentle and strange to the gas near the top and bottom. What exactly? We are still working out. There is also the question of the magnetic field strength. Measurements from the side suggest the polar field grows strong and quiet during the calm years of the solar cycle, then weakens and reverses as the next cycle builds. Some cycles the polar field is strong. Some cycles it is weak. A weaker polar field seems to point toward a weaker following cycle, but the link is not exact, and no one fully understands why one cycle gathers more polar strength than another. It is one of the small details that may turn out to be very large. Quiet things accumulate at the poles. Long, thin streamers of gas, faint as breath, rise from the polar corona and stretch outward into space. They are easier to see during an eclipse, when the bright disk is hidden and the soft outer atmosphere shows its true shape. From the side, those polar plumes look like the petals of some enormous silver flower opening into the dark. They drift, they sway, they fade. They carry pieces of the sun out into the wider solar system, where they slowly thin and vanish among the stars. It is humbling to think that this close to our own star, after centuries of watching, the top and the bottom remain mostly unseen. The little bright points, the tilted granules, the silver petals, the slow reversing field. These are the small details that may someday answer the larger questions. For now, they are just hints. Tiny grains of sugar scattered on a quiet pole. Beautiful, half understood, waiting patiently for us to look more closely. The story of how we first noticed the sun's slow heartbeat begins not with a great observatory or a famous astronomer, but with a quiet German pharmacist who simply liked to look at the sky. His name was Heinrich Schwabe, and in the early 1800s, he was searching for something else entirely. He believed there might be a hidden planet orbiting closer to the sun than Mercury, a small, dark world that would pass across the bright face from time to time. To catch it, he needed to watch the sun carefully, day after day, and note every dark spot he could see. He never found his planet, but he kept watching anyway, year after year, sketching the dark sunspots in a notebook with patient devotion. After 17 years of looking, he noticed something strange. The number of spots was not random. It rose and fell in a slow, steady rhythm, peaking and fading and peaking again. In 1843, he published his quiet finding, and the world began to realize the sun had a pulse. That pulse turned out to be about 11 years long, from minimum to maximum and back again. The sun seemed to breathe in slow motion. Other astronomers checked the old records, going back through centuries of sunspot drawings, and the rhythm appeared again and again. A Swiss astronomer named Rudolf Wolf gathered every observation he could find and built a long table of solar activity stretching back to the early 1600s. His numbering system is still used today. The discovery seemed simple at first. The sun had a cycle. You could almost set a clock by it. But the more carefully people looked, the stranger the pulse became. Some cycles were short, lasting only 9 years. Others stretched to 13 or 14. Some peaks were tall and violent, with sunspots crowding the face of the sun. Others were shy and small, barely rising above the quiet baseline. The heartbeat was real, but it was not steady. Then came another puzzle. In 1859, an English astronomer named Richard Carrington was sketching sunspots when he saw 2 brilliant patches of light flash across a group of dark spots. The flash lasted only minutes. Hours later, telegraph wires around the world began sparking and failing, and auroras lit up skies as far south as the Caribbean. Carrington had witnessed the first recorded solar flare, and he had connected it, however faintly, to events on Earth. The sun's cycle was not just a curiosity. It reached across space and touched us. In the decades that followed, astronomers built better instruments to track the rhythm. They learned that sunspots are cool, dark patches where strong magnetic fields push up through the surface. They learned that at the start of each cycle, the spots appear at high latitudes near the poles. And as the years pass, new spots emerge closer and closer to the equator. This slow drift, drawn on a chart, looks like the wings of a butterfly. It was first noticed in the late 1800s by an English astronomer named Edward Maunder and his wife Annie, who did much of the careful work of plotting it. Maunder also noticed something even stranger. When he dug through the old records from the late 1600s, the sunspots almost vanished. For roughly 70 years, the sun's pulse seemed to fade to nearly nothing. We will sit with that long silence in a later chapter. For now, it is enough to know that the heartbeat we thought was reliable had once, in living memory of our ancestors, simply stopped. Modern instruments have only deepened the mystery. We can now measure the sun's magnetic field across its whole face. We know the field flips direction at each cycle peak. So the true magnetic cycle is closer to 22 years. We know the rhythm is driven somehow by the swirling motion of plasma deep inside the sun, where hot gas rises and cool gas sinks, and the whole body rotates faster at the equator than at the poles. But the exact engine, the mechanism that ticks out 11 years again and again, is still debated. Some researchers favor models where the cycle is set by deep flows near the base of the convection zone. Others point to flows nearer the surface. Predictions for each new cycle's strength often miss the mark. So the pulse Schwabe noticed in his quiet pharmacy, with his small telescope and his patient sketches, is still a puzzle nearly 2 centuries later. We can count the beats. We cannot fully explain them. The sun keeps its rhythm mostly, and we keep listening, hoping the next cycle will tell us a little more about the engine hidden inside the light. There is a puzzle about the young sun that has troubled scientists for more than 50 years. It is one of those quiet contradictions that hides in plain sight, tucked into the rocks of Earth and the math of stellar physics. The puzzle is simple to state, but no one has fully solved it. When the sun was young, billions of years ago, it should have been much dimmer than it is today. And yet, the earth was not frozen. Liquid water flowed. Life began. Something does not add up. To understand the strangeness, picture the sun as it was about 4 billion years ago. It was the same star in the same place, but it shone with only about 70% of its current brightness. Stars grow slowly brighter over time as they burn through their hydrogen and shift their inner balance. This is one of the most settled ideas in stellar science. By the rules we trust, the early Earth should have been a frozen ball, locked in ice from pole to pole. The oceans should have been solid. The young world should have been a quiet white marble in the dark. And yet the rocks tell a different story. Ancient layers of stone, laid down by water more than 3 billion years ago, hold the fingerprints of rivers and shallow seas. Tiny fossils of early life appear in sediments that could only form in liquid water. The geology is clear, even if the cause is not. Somehow, on a world warmed by a dimmer star, the water stayed soft, and the chemistry of life kept moving. This is the faint young sun puzzle. The sun was weaker. The earth should have been frozen. The earth was not frozen. The pieces do not fit, and scientists have been trying to make them fit for decades. One idea is that the early Earth held a thicker blanket of greenhouse gases. Carbon dioxide and methane trap heat by catching infrared light before it can escape into space. If the young atmosphere held far more of these gases than it does today, the extra warmth could have made up for the weaker sunlight. This is the most popular answer, and it has support from some chemical traces in old rocks, but the numbers are stubborn. Some studies of ancient minerals suggest there was not enough carbon dioxide in the air to do the job alone. Methane helps, but methane breaks down quickly under sunlight. The math comes close, but it does not quite close the gap. Another idea is that the early Earth was simply darker. A world with fewer clouds, or with less ice, would absorb more of the sunlight that did arrive. If the young planet had little reflective surface, the small amount of warmth it received would have soaked in more deeply. Some researchers have explored this carefully, looking at how clouds might have behaved over a warmer ocean. Other researchers push back, pointing out that clouds are tricky things, and that small changes in their height or thickness can flip the warming the other way. A more daring possibility is that the sun itself was different. Some have wondered whether the young sun was slightly more massive than we assume, and and shed that extra mass slowly through a stronger solar wind. A heavier young star would have been brighter, easing the puzzle. The trouble is that we have very little evidence for this. Young stars we observe in the sky do lose mass, but not in the amounts this idea would need. It remains a quiet possibility, not a proven one. There is also the question of Mars. Mars shows clear signs of ancient rivers and lakes, carved into its surface when the sun was even fainter. Mars sits farther from the sun than Earth, so it should have been even colder. Whatever warmed the early Earth may have warmed Mars too. And whatever model we choose has to explain both worlds at once. So far, no single picture does this cleanly. What makes this puzzle so soothing to think about is how patient it is. The contradiction has waited inside the rocks for billions of years. The sun shone, the earth warmed somehow. Life took hold, and the question only formed much later, when humans learned enough to notice the gap. We look back across that vast stretch of time and see a star that should have left us frozen, and a world that quietly refused. The sun's past keeps a secret about how it once warmed a younger Earth, and the answer may lie in chemistry, in clouds, in the star itself, or in something we have not yet thought to look for. For now, the puzzle simply rests in the old stones, waiting. During a total solar eclipse, when the moon slides perfectly across the bright face of the sun, something quiet and strange becomes visible. A soft, pearly halo blooms into view around the dark disk. It is not a single ring of light, but a tangle of feathers and streamers, pale as frost, reaching out into the sky for millions of miles. This is the corona, the sun's outer atmosphere, and for most of human history, we could only see it during these brief moments of shadow. For all its beauty, the corona is a deep puzzle. It is far thinner than the surface below it, so thin it would feel like empty space to your skin, and yet its gas is heated to more than 1,000,000 degrees, while the visible surface sits at only about 10,000. The thin outer air of the sun is hundreds of times hotter than the bright layer beneath it. By every rule of common sense, this should not be possible. Heat should flow outward from the hot core and cool as it travels. Instead, somewhere between the surface and the corona, the temperature jumps upward like a fire lit in an empty room. This is the coronal heating problem, and it sits at the center of solar science. Many ideas have been offered, but none has won the argument. One leading theory says the heating comes from countless tiny flares, far too small to see one by one. These nanoflares, as some researchers call them, might pop and crackle across the surface like static, each one tiny, but together pouring enough energy into the corona to keep it glowing white hot. A competing theory points instead to magnetic waves. In this view, the sun's tangled magnetic field carries energy upward like a rope being shaken, and that energy unwinds into heat high above. Both ideas have supporting evidence. Neither has closed the case. The mystery matters because the corona does not stay put. It leaks. A steady breath of charged particles flows outward from it in every direction, filling the space between the planets. This is the solar wind, and it touches everything. It shapes the long blue tails of comets, pushing their dust and gas away from the sun. It carves the thin air of Mars, slowly stripping it into space over billions of years. It presses against the magnetic field of Earth, stretching it into a long teardrop on the night side of our world. When that wind grows stronger, the connections become easier to see. Gusts of solar plasma slam into Earth's magnetic shell and pour energy down into the upper atmosphere. The skies above the poles light up in slow green and red curtains, the auroras, painted by particles that began their journey in the corona. The same gusts can warm and swell the outer edge of our atmosphere, tugging gently on satellites and changing how radio signals bend around the planet. The sun's quiet outer glow, so faint we need an eclipse to see it, ends up writing itself across our daily lives in ways most of us never notice. The reach goes further still. The solar wind blows outward past every planet, past the icy bodies beyond Neptune, and finally meets the thin gas drifting between the stars. Where the two press against each other, they form a vast bubble around the entire solar system. Inside that bubble, we are partly shielded from the harsher radiation that fills the wider galaxy. The corona, in a sense, blows the walls of our home. How thick those walls are, how steady they remain, and how they change as the sun's mood shifts across the centuries, are all questions still being studied. Even the climate of Earth listens, in a faint way, to the corona's pulse. When the sun is more active, its wind grows stronger and deflects more of the cosmic rays that arrive from deep space. Some researchers wonder if this changes cloud formation in small ways. Others argue the effect is too weak to matter against the larger forces shaping our weather. The debate continues, careful and slow, with no clear winner. So the ghostly glow we glimpse during an eclipse is not just a halo around a star. It is the beginning of a long, invisible thread that ties the sun to comets, to planets, to auroras, to satellites, to the very boundary of our solar bubble. And at the heart of that thread sits an unsolved riddle. Why is the corona so impossibly hot? We have theories, instruments, probes diving closer than ever before. We do not yet have an answer. For tonight, it is enough to picture that pale crown quietly breathing across the dark. Above the sun's bright face, something strange is always happening. Great arches of glowing gas rise up from the surface, curve through the thin air of the corona, and then sink back down again. These are the plasma loops. They are made of charged gas, lifted and shaped by invisible magnetic lines, and they are some of the most beautiful structures in the solar system. A single loop can be larger than 10 Earths placed end to end. Some are small and faint, lasting only minutes. Others are huge and steady, holding their shape for hours or even days. They glow in colors our eyes cannot see, in the deep ultraviolet and soft X-ray light that special telescopes pick up from space. To those instruments, the sun looks less like a smooth ball and more like a tangled garden of bright, looping threads. These loops are not still. They tremble, they shift, they lean. Sometimes two loops drift close to each other and snap together, releasing a flash of energy. Sometimes a loop swells, brightens, and breaks open at the top, sending a stream of hot gas into space. And sometimes, for reasons we still cannot fully explain, a loop simply fades. Its glow softens its shape blurs, and then it is gone, as if the sun had quietly exhaled. This vanishing is one of the gentler puzzles of solar science. The plasma inside a loop should not just disappear. Matter does not work that way. The gas must go somewhere. One idea is that the loop slowly cools, and the glowing particles drift down along the magnetic lines, settling back into the lower atmosphere where they are no longer hot enough to shine. Another idea is that the magnetic field itself rearranges, opening the loop at one end so the plasma drains away into the solar wind. Both ideas may be partly true. The full picture remains open. What makes the loops even more interesting is that they seem connected to the larger heating mystery. Inside them, the gas reaches temperatures of 1 or 2 million degrees, far hotter than the surface below. Some researchers wonder if the loops act like tiny ovens, where countless small magnetic events release energy in quick bursts. Others wonder if waves traveling along the loops carry energy upward from deeper layers. The loops may be where the corona's strange heat is born, or they may simply be the places where that heat becomes easiest to see. We do not yet know which. Across centuries, our view of these arches has changed in slow, patient steps. Early astronomers, looking only with their eyes during total eclipses, saw soft streamers reaching out from the sun. They had no idea those streamers were shaped by magnetism. Later, photographs taken during eclipses showed more detail, hinting at curves and bridges in the pale outer light. The true loops, with their precise arcs, were not really seen until telescopes were lifted above the atmosphere, where the soft, ultraviolet light from the corona could reach a camera without being blocked by air. Each new mission has shown the loops in finer detail. We have watched them shimmer in slow motion. We have measured their temperatures, their densities, their movements. And the closer we look, the more we notice that the loops are made of even thinner strands, like ropes braided from glowing threads. Some of those threads may be no wider than a few 100 kilometers, which sounds large until you remember the sun itself is nearly 1.5 million kilometers across. Right now, the loops are changing in a way we can almost watch in real time. As the sun moves through its current cycle of activity, the number of loops grows and shrinks. They cluster around sunspots, lean toward the equator in some years, and toward the poles in others. Their shapes record the deep magnetic moods of a star that never quite settles. By the time you fall asleep tonight, loops you will never see have already formed, twisted, and faded somewhere above the solar surface. The truth is, no one has ever traced a single loop from its birth to its quiet end with complete certainty. We catch glimpses. We piece together patterns. We build models that match some of the behavior some of the time. But the loops keep their secrets gently, the way clouds keep theirs, shifting before you can name their shape. They remind us that even the most familiar star in our sky is still doing things we do not fully understand, drawing slow, bright arches above itself. And then, in the soft language of plasma and magnetism, letting them go. When you look at a picture of the sun taken in certain kinds of light, you sometimes see strange dark patches. They sit on the bright disk like quiet bruises, or like windows opening into something deeper. These patches are not really dark in the way a shadow is dark. They are simply cooler and thinner than the glowing plasma around them. We call them coronal holes, and they are some of the most beautiful and puzzling features the sun shows us. A coronal hole is a region in the sun's outer atmosphere where the magnetic field opens up and stretches away into space. In most of the corona, magnetic field lines arch back down to the surface, trapping hot plasma in glowing loops. But inside a coronal hole, the field lines do not loop. They reach outward like long pale threads, and they let the plasma escape. So in ultraviolet light, where bright loops would normally shine, you see only a soft, dim hush. The light from these regions tells a careful story. In visible light, coronal holes are almost invisible. The sun's photosphere, the surface we usually picture, shines straight through and gives no hint of them. But shift the wavelength. Look in extreme ultraviolet or in soft X-rays, and the holes appear suddenly, like ink poured into clear water. The sun reveals different layers depending on the color we choose. Each color is a different depth, a different temperature, a different question. Inside a coronal hole, the plasma is still hot by any earthly measure. hundreds of thousands of degrees, sometimes more, but it glows less because there is less of it, and because what is there is streaming away. The escaping particles form a fast branch of the solar wind, while the slow solar wind drifts off at around 400 kilometers per second. The wind from coronal holes can race outward at twice that speed or more. Where these fast streams lead, and why they accelerate so smoothly, remains one of the open puzzles our instruments are still trying to answer. One idea is that small magnetic disturbances near the base of the holes give the plasma tiny kicks. Wave after wave, the kicks add up, and the particles climb away from the sun's gravity. Another idea suggests that bursts of reconnection, where tangled magnetic threads snap and rearrange, fling plasma upward in countless small jets. The Parker Solar Probe has flown closer to the sun than any craft before it, and it has seen strange S-shaped bends in the magnetic field called switchbacks. Some researchers wonder if these switchbacks are the fingerprints of those small jets. Others think they form farther out as the wind travels. The evidence is incomplete. The light from coronal holes also paints a pattern across time. Near the quiet years of the solar cycle, big holes often sit near the sun's poles, like two pale caps. As the cycle grows more active, holes wander toward the equator, sometimes stretching in long dark fingers across the disk. When one of these equatorial holes faces our planet, the fast wind it sends out can reach us in a few days. It nudges the magnetic bubble around the Earth, sometimes painting the polar skies with auroras, sometimes barely whispering against the upper atmosphere. What the light cannot quite show us is the inner machinery. We see the dark patch. We see the streams flowing out. We do not yet see in full detail the moment a field line opens, or the precise way a plasma parcel decides to leave the sun forever. The corona is thin and hot and strange, and the physics there is not the physics of ordinary gases. It is the physics of charged particles dancing along invisible magnetic ropes. Models try to capture it. The models often disagree. There is something quiet and almost gentle about coronal holes. Even though they feed the fastest winds in the solar system, they look still on the images. They drift slowly across the face of the sun as it rotates, taking about 27 days to come around. In their soft darkness, you can sense the sun breathing outward, releasing material into the wider neighborhood, threading its substance through the planets and beyond. Where do these streams lead? They lead past the Earth, past the gas giants, past the icy edges of the outer worlds, and onward into the bubble the sun blows around itself. They thin out, they tangle with the wind from other directions. They finally meet the matter between the stars. The light shows us the opening. The opening shows us the road. And the road, for now, still holds quiet stretches we have not fully traveled with our minds. The sun does not whisper to us in words. It writes its history into things we can read long after the storms themselves have faded. Tree rings hold one record. Ice cores hold another. Inside each frozen layer, deep beneath the polar caps of Greenland and Antarctica, there are tiny traces of atoms that only form when something violent happens far above the Earth's atmosphere. When the sun hurls out a great burst of energy, the rain of particles changes the chemistry of the air. That changed chemistry drifts down, settles into snow, and waits for someone to find it thousands of years later. In the year 774, something extraordinary happened to our star. We know this because the trees remember. Old wood from that year shows a sharp spike in a form of carbon called carbon-14, which builds up in the atmosphere when high-energy particles slam into nitrogen. The spike is enormous. It dwarfs anything seen in modern times. A second event, slightly smaller, shows up around the year 993. There may be even older ones, hidden deeper in the rings of ancient trees and the layers of ancient ice. No one alive saw these storms. No telescope recorded them. And yet the sun left its signature in the wood and in the snow, a kind of fingerprint pressed into the slow biology of the world. What caused these events remains an open question. One idea is that the sun produced a flare far larger than anything we have measured directly, a so-called superflare, dumping a vast wave of particles toward Earth in a matter of hours. Another possibility is that several big storms landed close together in time, stacking their signatures into what looks like a single sharp spike in the records. A third theory points outward, suggesting some of these spikes might come from distant cosmic sources rather than the sun itself. The evidence is incomplete. The trees only tell us that something happened, not exactly what. Scientists have learned to turn solar data into sound. Spacecraft like the Parker Solar Probe carry instruments that pick up the trembling of plasma and the rippling of magnetic fields. These signals are not sound in the everyday sense, since space carries no air to vibrate, but the patterns can be shifted into a range our ears can hear. When researchers do this, the solar wind becomes a low, breathy hiss, like wind moving through a long tunnel. Sudden shocks become muffled thumps. Magnetic switchbacks, those strange folds in the sun's outgoing field, become small clicks and pops, as if something is gently knocking against the inside of the probe. The sun itself rings like a bell in its own slow way. Inside the star, hot gas rises and falls, and these motions create pressure waves that bounce through the interior. The surface lifts and drops by tiny amounts on cycles measured in minutes. When scientists turn these oscillations into audible tones, they hear a deep, layered hum, a chord built from millions of overlapping notes. This field of study is called heliosismology, the science of reading the sun by its vibrations, much the way geologists read the earth by its quakes. The hum is steady. It changes slowly with the seasons of the solar cycle, and it carries clues about what is happening in regions of the sun we will never see directly. What we cannot hear is the long boom of those ancient storms. The events of 774 and 993 left no sound, only chemistry. We have no recording of the sky lighting up, no diary entry from a watching eye that understood what it saw. There are scattered medieval mentions of red skies and strange auroras, but it is hard to know which lights belonged to which storm. The match between the records and the rings is still being worked out. Some researchers believe future digging through old wood and ice will reveal a pattern, a rhythm to these monster events. Others suspect they are nearly random, rare bursts with no schedule we can guess. If a storm of that size struck today, modern instruments would hear it everywhere. Satellites would shudder. Power grids might falter. The auroras would slip far down from the poles, painting skies that have not glowed in 1,000 years. Whether such a storm is overdue, or whether we are simply living in a quiet stretch between them, no one can say with confidence. The sun keeps its own calendar. The wood remembers. The ice remembers. And somewhere in the deep records, still buried under glaciers, there may be older echoes we have not yet found, waiting for the right hand to lift them out of the dark. To understand the sun, it helps to step back and look at where it sits among the other stars. The night sky holds so many points of light, and each one is a sun of its own. Some are bigger, some are smaller, some burn hotter and bluer, some glow cool and red. Our star sits somewhere in the middle of all that variety, and the simple numbers that describe its place are quietly beautiful. Astronomers sort stars by their light and their heat. They use a chart that lines stars up by color on one side and brightness on the other. Most stars in the sky, including the sun, fall along a gentle curve called the main sequence. This curve is just a pattern. It shows that brighter stars tend to be hotter and bluer, while dimmer stars tend to be cooler and redder. Our sun sits in the middle of this curve, glowing a soft yellow-white, about 10,000 degrees Fahrenheit at its visible surface. In the language of stars, the sun is called a G-type main sequence star. The letter G is part of an old system that sorts stars by color and temperature. Stars hotter than the sun get letters like F, A, B, and O cooler stars get K and M. Each letter folds into the next like a slow gradient, a rainbow stretched across the galaxy. The numbers around the sun feel almost too tidy to be real. It takes light from the sun about 8 minutes and 20 seconds to reach Earth. That distance, 93 million miles, is called one astronomical unit. Astronomers use it as a ruler for the whole solar system. Jupiter sits about 5 of those units out. Neptune, about 30. The nearest other star, Proxima Centauri, sits more than 260,000 of those units away. Light from it takes a little over 4 years to reach us. Even the rotation of the sun follows quiet patterns. Its equator spins once every 25 days. Its poles take closer to 35. This uneven spin is called differential rotation, and it slowly winds the sun's magnetic field like thread on a spool. Out of that winding, the 11-year cycle seems to emerge. The numbers are clean. The reason behind them is not. Astronomers also search for stars that look like the sun in almost every way. They call these solar twins. A true solar twin matches the sun's mass, temperature, age, and chemistry within a narrow window. A handful have been found within a few hundred light years of Earth. Some of them spin faster than the sun. Some spin slower. Some have magnetic cycles like ours. Others seem to have none at all, or cycles much shorter or much longer. This is where the elegant math runs into an open question. If the sun is just one G-type star among many, its 11-year cycle should be common. Yet when astronomers measure the brightness flickers of other sun-like stars, the variety is wider than expected. Some sit in long, quiet stretches. Some flare more strongly than ours ever has in recorded history. One idea is that the sun's cycle is fairly typical, and we simply have not watched other stars long enough to see their full rhythm. A competing view holds that our sun may be unusually steady, a calm star among more restless cousins. The evidence so far does not pick a clear winner. The numbers stretch even further when you consider the sun's place in the Milky Way. Our star sits about 26,000 light years from the galactic center, riding along one of the spiral arms. It circles the heart of the galaxy once every 230 million years or so. The last time the sun was in this same spot, dinosaurs had not yet appeared on Earth. Inside the sun, the math runs deeper still. Every second, about 600 million tons of hydrogen fuse into helium in the core. A small slice of that mass turns into pure light and heat, following the simple ratio between energy and mass that Einstein wrote down a little over a century ago. The same rule that governs our star governs every star you can see. What makes all of this soothing rather than overwhelming is how orderly it is. The orbits can be predicted to the second. The distances follow gentle rules. The colors and temperatures line up along a smooth curve. The universe seems to run on a small set of simple instructions. And yet, when we look closely at our own sun among its many cousins, the simple instructions still leave room for surprises we cannot yet explain. The numbers are clear. The story they are telling is not finished. Between the years 1645 and 1715, something strange happened to the sun. The sunspots, those dark wandering marks that usually drift across its bright face, almost completely vanished. For 70 long years, astronomers who watched the sun through their early telescopes saw a face that was nearly blank. They kept careful drawings. They counted what they saw. And what they saw was a quiet sun, far quieter than the one we know today. This long pause is now called the Maunder minimum, named after the husband and wife team who later studied those old records. During that same stretch of time, parts of Earth grew strangely cold. Rivers in Europe froze in winters that had once been mild. Crops failed in places where they had grown for centuries. Painters of that era often showed people skating on rivers that no longer freeze at all. The period is sometimes folded into a broader cold stretch called the Little Ice Age. The question that still hangs over solar science is whether these two things were truly linked. Did the quiet sun cool the earth, or were the frozen rivers caused by something else entirely, like volcanic ash high in the air, or shifts in ocean currents that had nothing to do with the star above? Some researchers believe the sun played a real role. Others think its effect was small, and that the cold years had many causes layered together. The honest answer is that we do not yet know how much weight to give each piece. What makes the Maunder minimum so haunting is how delicate it makes everything feel. The sun pours out a steady stream of light and heat. Earth catches just a tiny sliver of that flood. We sit at a distance that lets water stay liquid on the surface. A little closer, and the oceans would boil away. A little farther, and they would freeze solid. The thin shell of air around our planet traps just enough warmth to keep the nights from killing us, but not so much that the days bees roast everything alive. Into this careful balance, the sun adds its own small wobbles. Across each 11-year cycle, the total light it sends out changes by only about 0.1%. That sounds like nothing. And yet, when the sun grows quiet for decades on end, the slight dimming, the change in ultraviolet light, the shift in the solar wind, all of it seems to nudge the climate in subtle ways. How those nudges travel through clouds, oceans, and air is still being worked out. Some studies point to changes in the high upper air. Others point to shifts in the patterns of storms. The threads have not yet all been pulled together. There is also a deeper unease in the Maunder records. We have no firm idea why the sun went quiet then, and no firm idea whether it might do so again. The 11-year cycle is real, but it is not perfectly regular. Some cycles are strong, some are weak. Every so often, the rhythm seems to falter, as if the engine deep inside the star is holding its breath. We can describe these pauses after they happen. We cannot yet predict them in advance. It is worth sitting with how thin the margins are. The atmosphere that shields us from the solar wind is only a few 100 kilometers thick, and most of its mass lies in a layer thinner than the distance many people drive to work. The magnetic field that wraps around Earth and turns aside the worst of the solar storms is invisible, generated by molten iron moving deep in the core. Any one of these pieces, slightly different, and the story of life here would not have been written. The sun, for all its steadiness, is part of that balance. It has been a patient companion for more than 4 billion years, glowing with what looks like calm constancy. But the Maunder minimum reminds us that the calm is not perfect. The star flickers. It pauses. It changes in ways we are still learning to read. One possibility is that long, quiet spells like the Maunder are simply the natural breathing of a complicated magnetic engine, and they will come and go for as long as the sun shines. Another possibility is that there are patterns hidden in the data we have not yet uncovered, patterns that might one day let us see a quiet stretch coming. For now, the record is too short and the engine too deep. We watch, we wait, and we hold the thought that our warm, lit world rests on a balance more fragile and more mysterious than it usually seems. Far beyond the bright disk of the sun, far beyond the planets and their cold orbits, there is a quiet boundary. It is not a wall. It is not a shell. It is more like the soft edge of a long exhale. The sun is breathing, in a sense, and the breath it gives off shapes a vast bubble around our entire solar system. This bubble has a name. It is called the heliosphere, and we still do not fully know its shape. The heliosphere is made of solar wind. That is the steady stream of charged particles the sun releases in every direction, all day, every day, year after year. As this wind pushes outward, it carves a pocket inside the thin gas that drifts between the stars. Inside that pocket sits the sun, the planets, the comets, and us. Outside the pocket lies the wider galaxy, the boundary where the solar wind finally slows and meets the gas of interstellar space is called the heliopause. Only 2 spacecraft have ever crossed it, and what they found raised more questions than it answered. For a long time, scientists pictured the heliosphere as a comet shape. They imagined a round head facing the direction the sun moves through the galaxy, and a long flowing tail trailing behind. It was a simple and graceful idea, but newer measurements have made that picture uncertain. Some readings suggest the bubble may be more rounded, almost like a soft sphere with a slight bulge. Others hint at something stranger, with 2 lobes or a crescent shape. The truth is, we have never seen the heliosphere from the outside. We are inside it, looking out, trying to map a room by feeling its walls in the dark. One theory says the tail is long, stretching for many billions of miles behind us as we drift through the galaxy. Another theory says the tail barely exists at all, because magnetic forces curl the solar wind back on itself before it can flow very far. Both ideas come from careful work. Both fit some of the data. Neither fits all of it. The question of whether our home has a tail and how long that tail might be remains open. The heliosphere matters for reasons that go beyond simple curiosity. It acts like a soft shield. The interstellar gas outside is laced with high-energy particles called cosmic rays, racing in from distant supernovas and other violent events across the galaxy. The sun's bubble slows many of them down before they reach the inner planets. When the sun is active, the bubble pushes outward and the shield grows stronger. When the sun is quiet, the bubble shrinks a little and more cosmic rays slip through. How much this shield has changed over the long history of Earth is something we are only beginning to study. There is a deeper mystery, too. The size of the heliosphere depends on the strength of the solar wind, and the solar wind depends on processes inside the sun that we still cannot fully predict. If the sun went through a long, quiet spell, like the Maunder minimum centuries ago, the bubble might pull in closer. If the sun were unusually active for a stretch of time, the bubble might swell. We do not know how much the heliosphere has grown and shrunk over the ages, or how those changes shaped the planets it surrounds. The two spacecraft that crossed the heliopause sent back signals from a region no human machine had ever touched. They found that the magnetic field on the other side was tilted differently than expected. They found that some particles flowed in patterns no one had predicted. The data did not confirm the old models. It did not confirm the new ones either. It simply added new puzzles to the pile. There are ideas for future missions that would travel out and look back, taking the first true picture of our bubble from the outside. Such a journey would take many decades, perhaps longer than a human lifetime. For now, we work with hints. We work with the thin trickle of measurements from probes that are very far away and growing fainter each year. We work with models that disagree. It is a gentle thing to think about as the night settles in. We live inside a soft shape we have never seen. The sun breathes outward, and that breath holds back the cold wind of the galaxy. The walls shift, the shape changes, and somewhere out beyond the planets, in the quiet dark, the boundary of our small bubble drifts, unmapped, waiting to be understood. The sun we know tonight is a star in the middle of its long life. It has been burning for about 4.5 billion years, and it has roughly that much time again before its story takes a sharp turn. In between now and then lies a future no one has fully written. The sun will keep changing in small, slow ways, and and some of those changes we still cannot predict. In the next million years, the sun will look almost the same to anyone gazing up at it. Its brightness will drift only a little. Its cycle of sunspots will likely keep pulsing, though perhaps with quiet centuries scattered between busy ones. We do not know when the next long calm will arrive or how deep it will go. We do not know if the cycle itself is fully steady or if it slowly shifts over tens of thousands of years in ways no human has yet watched. Across 100 million years, the changes grow easier to see. The sun is slowly brightening as it ages. Each billion years, it shines a little more strongly than before. Most models suggest that in roughly a billion years, the sun will be bright enough to push Earth's climate past a point of no return. The oceans may begin to boil away into the sky. Whether life finds a way to endure or move or end is one of the deep, open questions of our planet's future. Yet, the sun itself will hardly notice. To a star, a billion years is a chapter, not an ending. It will keep fusing hydrogen in its core, slowly turning that light fuel into heavier helium. The core will grow denser. The outer layers will swell, gently at first, then more and more. Somewhere around 5 billion years from now, the sun will run low on hydrogen at its center. What happens next is part theory, part careful guesswork. The leading idea is that the sun will swell into a red giant, a vast, cool star many times its current size. Its outer edge may reach past the orbit of Mercury, perhaps Venus, perhaps even Earth. Some models say Earth survives, pushed outward as the sun loses mass. Other models say Earth is swallowed and dissolved into the star's thin outer layers. Both possibilities remain on the table. After the red giant phase, the sun is expected to shed its outer shells in slow, glowing waves. These waves will drift outward as a soft nebula, lit from within by the hot core left behind. That core will become a white dwarf, a tiny, dense ember about the size of Earth, but holding most of the sun's mass. It will glow for many billions of years, fading slowly, cooling toward darkness. No one has ever seen a white dwarf cool all the way to black. The universe is not old enough yet. while the sun is moving through these long acts, the wider sky will be changing too. Continents on Earth will drift, collide, and reshape themselves many times over. Nearby stars will pass by, some close enough to nudge distant comets loose. New stars will be born in nearby clouds of gas. Some of the stars we see tonight will burn out. Others, still hidden inside their nurseries, will one day shine bright in skies no human eye will ever read. Galaxies move as well. The Milky Way and the Andromeda Galaxy are drifting toward each other. In a few billion years, they may begin to merge into a single larger galaxy. The sun will likely still be shining during that slow dance, though where it ends up within the new galaxy is uncertain. Stars rarely collide in such mergers. The space between them is too vast, but the night sky from any world orbiting the sun would look entirely different, full of new arcs of light. How much of this can we really know in advance? The broad outline is supported by what we see in other stars at different stages, but the small details, the exact timing, the precise path remain open. Stars are not clocks. They wander, brighten, dim, and sometimes surprise us. The sun has been steady on human timescales, yet we have only watched it closely for a few hundred years. Its longer rhythms are still mostly hidden. So the sun's future is partly written and partly blank. The chapters far ahead are sketched in pencil, waiting for evidence we may never gather in any single lifetime. For now, the star above us keeps turning, keeps humming, keeps shedding light onto a world that grew up beneath it. Tonight it is simply our sun, going about its quiet, ancient work. So now we step back, all the way back, and let the sun become small again. A single warm point of light among the hundreds of billions of stars that drift through our galaxy. One of perhaps 2 trillion galaxies in the part of the universe we can see. And yet, for all that smallness, this single star is the only one we will ever study so closely. The only one we can watch breathe. Think of what we have learned, and how much of it still ends in a question. We have built telescopes that float in space and watch the sun without blinking. We have sent a small probe to fly through the edges of its atmosphere, closer than anything we have ever dared. we have listened to the soft hum of its inner waves and mapped the slow churn beneath its skin. And still, after all of that, we cannot say for certain why the corona glows so hot. We cannot say with confidence what the next cycle will bring. We cannot fully predict the next great storm. Some of these answers may come soon. New instruments are being built that will watch the sun in finer detail than ever. Ground telescopes that can resolve features only a few dozen miles across on the solar surface. Spacecraft that will study the poles at last, those quiet regions we have barely glimpsed. Each of these tools is a fresh pair of eyes. Each one might catch the small clue we have been missing. Yet, other answers may take generations. The solar cycle is so slow and so strangely variable that a single human lifetime may only see 7 or 8 of them. To understand its longer rhythms, we may need centuries of careful watching. The Maunder minimum, that long, quiet stretch from the 17th century, still puzzles us because we did not have the instruments back then to record what we now wish we knew. The sun keeps a longer diary than we do, and there is a deeper thought waiting here, the one that often comes just before sleep. The atoms inside the sun are the same atoms inside you. The hydrogen burning at its core is the same hydrogen that drifts in the water of your blood. The heavier elements scattered through your body, the iron, the calcium, the oxygen, the carbon, all of these were forged inside earlier stars that lived and died long before our sun was born. When those ancient stars ended, they scattered their ash into the dark. That ash drifted for ages. Some of it gathered slowly into the cloud that became our solar system. Some of it became the ground beneath your feet. Some of it became you. So when we wonder about the sun, we are also, in a quiet way, wondering about ourselves. The same physics that lights the corona warms your skin in the afternoon. The same magnetic threads that arch above sunspots are cousins to the tiny magnetic fields humming inside the wires of any machine you have ever used. The same gravity that holds the sun together holds the moon in its slow circle and pulls the tide of the oceans and presses you gently into your bed tonight. It is a humbling thought and also a comforting one. The questions our instruments cannot yet answer are not failures. They are the open spaces where future minds will go. Someone, perhaps not yet born, will look at data we cannot collect. With eyes trained by lessons we have not yet learned, and they will see what we could not. They will find the missing piece of the coronal puzzle. They will read the longer rhythms of the cycle. They will understand why this particular star, our star, behaves the way it does. And perhaps even then, new questions will rise to take the place of the old ones. That is how this kind of wondering works. Every answer opens a door, and behind that door is another room, softly lit, full of new things to ask. The sun has been shining for over 4 billion years. It will shine for about 5 billion more. There is time. There is, in the largest sense, more time than we can hold in our minds. For tonight, the wondering is enough. The sun is out there, on the other side of the world, still burning, still humming with waves we have not yet decoded, still throwing its slow wind into the dark. Tomorrow it will rise again, as it has every morning of your life, as it did long before any human eye was here to see it. And we will keep asking gently what it is and how it works and why it is the way it is. We have wandered a long way together tonight. We started at the bright surface of a star we thought we knew, and we ended up holding a handful of beautiful, unfinished questions. That is, perhaps, the truest gift the sun gives us. Not certainty, not a tidy answer, just a steady invitation to keep wondering. Picture, for a moment, the earth from far away. A small blue world, turning slowly in the dark. Its oceans are calm tonight on one side, lit by a soft white moon. On the other side, the daylight fades into long golden light, and somewhere a field of tall grass bends gently in the evening wind. From this distance, you cannot see the cities or the roads or the worries of the day. You can only see a quiet planet held in place by a steady, glowing star. That star, the sun, is doing what it has done for more than 4 billion years. It is burning slowly. It is breathing out its wind. It is humming with sound waves we cannot hear, and weaving magnetic threads we cannot fully map. And somewhere above its bright surface, in that thin, ghostly crown of light, the gas is heated to temperatures no one has fully explained. The question is still open. The mystery is still alive. Think of how strange and wonderful that is. We have built spacecraft that dive into the corona. We have watched the sun through every color of light. We have counted its sunspots for 400 years. And still, the deepest questions remain. Why is the outer air hotter than the surface beneath it? Why does the 11-year cycle sometimes skip a beat? Why did the sun fall quiet during the long stillness of the Maunder minimum? We do not know. Not yet. There is a soft comfort in that. The universe is not finished telling its story, and we are not finished listening. Imagine, somewhere out beyond the orbit of Neptune, the solar wind is still flowing. It is thin now, and slow, and cold. It pushes outward into the dark, drawing the bubble of the heliosphere around us like a blanket. Beyond that boundary lies true interstellar space, where the wind from other stars begins to mix in. We live inside a vast, gentle shelter we did not build, a shelter our star blows around us every second of every day. And inside that shelter, on this small blue world, you are lying still. Your breathing is slow. The room is quiet. The sky above your roof holds the same stars that puzzled the first astronomers, and the same sun that will rise in the morning, whether or not we ever solve its mysteries. Picture a galaxy turning far from here, a wide spiral of soft light, its arms full of young blue stars and old red ones, drifting in a slow, patient circle. Each of those stars has its own corona, its own wind, its own cycle of quiet and storm. Each one is, in some small way, a cousin of our sun, and around many of them, perhaps, there are small worlds with calm oceans where someone else might be looking up tonight, wondering the same things we wonder. There is no urgency in any of this. The mysteries will wait. The sun will keep burning. The corona will keep glowing in its strange, unexplained heat. The sunspots will come and go on their slow, uncertain rhythm, and the questions we asked tonight will still be there in the morning, patient and gentle, waiting for the next pair of eyes to look up. For now, you do not need to solve anything. You do not need to remember anything. Let the questions drift away like soft clouds across a dark sky. Let the names seams of the theories blur. Let the numbers fade. What stays is the feeling of being small and safe inside a universe that is older and stranger and kinder than we sometimes remember. Outside your window, somewhere, the wind moves through trees. Somewhere, an ocean rests under moonlight, its waves slow and silver. Somewhere, the sun is shining on the other side of the world, painting the morning in soft gold. And here, in this quiet room, you are held by all of it. The turning planet, the steady star, the vast, gentle, unfinished sky. Let yourself rest now. The mystery does not need you tonight. The sun will burn just fine without your attention. And tomorrow, when you wake, the universe will still be here, still wondering with you. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet